In this video, we're going to start taking a look at another major integration technique, and this integration technique is called partial fraction decomposition. So, pretty big title, and we're just going to abbreviate it PFD, right? Now, in order to really understand the process of partial fraction decomposition, we have to know quite a bit about rational functions and polynomials. And I'll give you just a little recap of some of the highlights of what we need from those particular topics in algebra. But before I do that, I just want to give you an idea of what partial fraction decomposition is all about. So let's say I gave you two integrals and you get to choose which of the two you want to evaluate. So I'm going to write down one integral. Let's say it's 3 over x plus 4 minus 2 over, let's say, x minus 5 dx, right? And compare that to this one, x minus 23, and then over x squared minus x minus 20, right? And I say you have to do one of them, but you get to choose which one you do. And based on what we know about antiderivatives, which one do you think would be easier to work with, right? Well, so for instance, like this one, we might say, well, is there a u sub I could use? And typically when you have a fraction like this, you try to look at the denominator and see, well, if I differentiate this, do I get anything close to what I have in the numerator? And I'm not seeing it, right? Whereas over here, where I have these two separate fractions, well, I can think of this one as the integral of 3 over x plus 4 minus, oh, I'm sorry, let's split it into 2. And then we have dx, and then minus the integral of 2 over x minus 5 dx. So that's one property of the definite integral or indefinite integral we can use. And we can also factor out the 3. So I can take the 3 outside, and then I have 1 over x plus 4 dx. Take the 2 out, and then 1 over x minus 5 dx. And then I could say, can I think of a function that when I differentiate it, I'll get 1 over x plus 4? Well, that looks like a ln type function. So then this is 3 times the natural log of x plus 4 minus 2 times the natural log of x minus 5, and then our plus c. So I mean, that one wasn't too bad. But then still, I can't think of a way of how to do this, right? I don't see, like, certainly not integration by parts doesn't seem to work with this, because this function, it clearly isn't easy to integrate, so it's really, I couldn't use it as my dv. And then to differentiate this, it's just going to get way more complicated because I would have to use my quotient rule. Well, the thing about my choice is, they don't look like it, but these functions are identical, right? These functions are identical. And let me actually show you now by doing some algebra that if I take these two fractions, get the common denominator, and subtract them, I actually end up with this function right here, right? So let's do a little bit of algebra and take my 3 over x plus 4 minus 2 over x minus 5, and then the common denominator here would be the quantity x plus 4 times the quantity x minus 5, and then to get a denominator of x plus 4 times x minus 5 for this first fraction, multiply the top and the bottom by x minus 5. So I have this, and then minus. Do something similar for the second fraction. Multiply the top and the bottom by the quantity x plus 4. All right. And then if I distribute the 3, I'll get 3x minus 15. And then here, distribute the negative 2, I'll get a minus 2x minus 8. If I FOIL out in the denominator, I'll get an x squared, and then I have a plus 4x minus 5x, so that's minus x. And then positive 4 times a negative 5 is a negative 20. And then if I look carefully, so in fact, let me write it over here. So when I simplify the numerator, I have x minus 23 over x squared minus x minus 20. So in fact, I gave you the same function, but just in a different form. Here, the function was kind of written as a single rational function, and this is what we mean by a rational function. And over here, here it's written as the difference between two rational functions. And the process that we just went through, going from this form to this form, so that process there, it has lots of different names, but basically what we did, we combined these two separate fractions into one. So you can think of this as, maybe combining fractions. But what partial fraction decomposition? The word decomposition means you're going to break something that is a whole into parts. You're going to break a single fraction into lots of different, small, hopefully easier fractions that are either being added or subtracted. So what we're going to work on in this whole process is, if I gave you this, right, to integrate, we would have to learn a process of decomposing this rational function into the sum or difference of easier rational functions. So we're going to learn how to go this way, and that's the process of partial fraction decomposition, right? So again, and this is a process that is useful even outside of integration, right? It's our technique. It's a technique that we have to master for the purposes of evaluating certain integrals, but it goes beyond that. This skill of taking a single rational function and writing it as a sum or difference of two easier or smaller rational functions is a really, really important thing. All right, so that's what we're going to work on. But in order to do this process, and we're going to be utilizing certain terminologies and certain theorems from algebra that we need to be up to speed on. So just going to take a few minutes to do a little crash course in rational functions and certain properties of polynomials, right? So first, let's define, and again, I'll just kind of do this sort of as a bullet list. What is a rational function? Like, what is the formal definition of a rational function? Well, it's any function of this form, p of x over q of x, where p and q are polynomials, right? So p and q are polynomials. Now, I'm writing this down and I'm assuming we know what the definition of a polynomial is, right? And a rational function is when you divide two polynomials. Now, the p and or q, they could be constants, right? And then the whole thing just works out to be a constant, right? But it allows for non-constant polynomials. So for instance, all of these this x minus 23 over the quantity x squared minus x minus 20, that's an example of a rational function. The 3 over x plus 4 is a rational function. The 2 over x minus 5 is a rational function. All right. Now, a rational function is said to be proper. So you have a proper rational function. That's when the degree of the numerator, so I'm going to I'm going to use DEG as an abbreviation for degree. So the degree of P of X is strictly less than the degree of Q of X, right? So whenever the highest power in the numerator is less than the highest power in the denominator, we say that the rational function is proper. Otherwise, you get an improper rational function. So an improper rational function is one in which the degree in the numerator is greater than or equal to the degree in the denominator. So the degree of P of X is greater than or equal to the degree of Q of X, right? And depending on which one you're given in the problem, if you're given a proper rational function, then your solution starts out at one particular point. If you have an improper rational function, then your solution starts out doing a slightly different thing, right? So again, it's a series of steps, and you have to make sure that you understand when each step could possibly occur. So let's do just a couple examples of this. So if I have x plus 1 over x squared plus 1, this is proper, right? The degree of the numerator is 1. The degree of the denominator is 2. Therefore, 1 is less than 2. So we classify this as a proper rational function. If I have x plus 1 over x plus 2, this is now improper, because both the numerator and the denominator have a degree of 1. So even if the degrees are equal, right, or if we had like x squared plus 1 over x plus 2, both of these are examples of improper rational functions, right? So as long as the degree in the numerator is greater than or equal to the degree in the denominator, then we classify the entire function as a improper rational function. All right. So, let's kind of do another example. So you might have a function that looks like x squared plus x minus 4 all over x cubed minus 4x squared plus 8x minus 12. This would be something that is a proper rational function. And at the end of this process, we would like to be able to integrate a function that looks like this, right? That's our goal at the end of completing partial fraction decomposition, right? So to be able to integrate things like this. And again, so let's just say that this degree, that polynomial has degree 2, this polynomial has degree 3, hence proper, right? So, so that's the concept of, or the idea behind improper versus proper rational functions. Now, a big part of the partial fraction decomposition is the ability to recognize the different types of factors that a polynomial can have, right? So, and again, I'll illustrate a lot of these with examples. So let's say we take the polynomial x squared plus x minus 30. Well, this can be factored in the form x plus 5 and x plus 6, right? Now, each of these are linear factors, right? So this is a linear factor, this is a linear factor. A linear factor is a factor of the form ax plus b, right? So a factor is said to be linear if it is of the form ax plus b, where a and b are real constants, right? Now, a lot of times our a and b, they tend to be integers, but they don't have to be integers, right? So for instance here, this particular factor, the a is 1 and the b is 5. In this factor, the a is 1 and the b is 6. So this polynomial factors into a product of linear factors, right? Now, if you take a look at something like x squared minus 10x plus 25, this can be factored as x minus 5 times x minus 5. So here, the linear factor is repeated. Again, this is a linear factor, this is a linear factor, but it's actually repeated. So it's the same factor that shows up multiple times. And we use our exponential notation to indicate that it's just x minus 5 squared. So whenever the same factor shows up multiple times in the factorization of your polynomial, we say that that factor is repeated, right? So here, a factor that shows up multiple times, right, in a factorization, or let's say the factorization. Factorizations are not necessarily unique, but we'll just say the factorization. Let me get this off. So the factorization. So if it shows up multiple times in the factorization, is said to be repeated. So it's a repeated factor, right? The number of times that that factor is repeated is called the multiplicity. So the number of times a factor is repeated is called its multiplicity. Like how many of this actual factor is in the factorization, right? So we got multiplicity, repeated, right? So in this case, we can say that this polynomial has a repeated factor of x minus 5 with multiplicity 2, right? So let's write that down. So x minus 5 is a factor of x squared minus 10x plus 25 with multiplicity 2. And basically, it's that number that you can look at to say that you can use that number to identify the multiplicity. But that requires like a full factorization, and then you essentially, if you have a perfect square like this is, then you have the 2 there. If it's a perfect cube, you'll have a 3 there, right? Now, so if a factor shows up only once, right? If the multiplicity of a factor is 1, as in these two examples, we say that the factor is simple, right? Simple linear factor. So if the multiplicity of a factor is 1, we say the factor is simple, right? So we can have either simple linear factors like these, or we can have repeated linear factors like this one, all right? So let me give another example. Now I'm going to write down a sixth degree polynomial. And I'm sure you guys love to factor these types of polynomials, but 2x to the sixth plus 9x to the fifth plus 6x to the fourth minus 19x cubed minus 18x squared plus 12x plus 8. Now, one of the hardest things to do in math is to factor things, whether you're factoring like large integers and you're trying to find a prime factorization, or if you have polynomials of a very high degree. I mean, 6 isn't high, but it's higher than what we typically work with. Factoring is tough, but I happen to know the factorization of this polynomial. So it factors as 2x plus 1, and then x minus 1 squared, and then x plus 2 cubed, right? And so we can see this is the full factorization. And this one, so these are all linear factors, right? So these are all linear factors, the 2x plus 1, the x minus 1, and the x plus 2. These are all linear. But they each have a different multiplicity. The 2x plus 1 only shows up once in this factorization, and that's why it's raised to the first power. So 2x plus 1, and this has, I'll just say, with multiplicity 1. And then the x minus 1, it shows up twice. That's why it's raised to the second power. So this one has multiplicity 2, and then the x plus 2 happens to show up 3 times. So that's why it's raised to the third power. That means it has multiplicity 3, right? And again, a big part of the partial fraction decomposition process is to be able to come up with factorizations like this, right? Now, it turns out that there are some polynomials where we can't reduce it to just a product of linear factors. Sometimes the best we can do, if we're using only real numbers, the best we can do is to get a quadratic that can't be factored anymore, right? So, so using only real numbers, right? Polynomials may have quadratic factors, so they may have quadratic factors which can't be factored anymore, right? Which can't be factored further. These types of quadratic factors are said to be irreducible over real numbers, right? So these factors are said to be irreducible over the reals or over real numbers, right? If you were using complex numbers, then every polynomial can be broken down into a product of linear factors. But if we're using only real numbers, there are some quadratics that we can't break down anymore, right? So here's an example. Again, I'll give you another big one. Here's an 8th degree polynomial. So x to the 8th plus 10x to the 6th plus 36x to the 4th plus 54x squared plus 27. That is equal to this. X squared plus 1 times x squared plus 3 to the third power, right? Now, when you look inside, you see something that's not linear. We know it's not linear because we see this particular power, right? We can see that it's a quadratic, And the thing is, we can't factor this anymore. You can try, but you won't be able to find a factorization using real numbers. So for instance, so both of these now, let me write these down. So the x squared plus 1 and the x squared plus 3, these are what we call irreducible quadratic factors, right? And they also have multiplicities. So again, it's fully factored now. You can see that the x squared plus 1 is raised to the first power. So this one has multiplicity 1. And then the x squared plus 3, that shows up 3 times. So it has multiplicity 3, right? Now, the question is, so how do we know when a quadratic factor is irreducible? So like if you write down the general quadratic, how can we tell, right? Well, there is a concept associated with the quadratic known as the discriminant. You might remember that. So let's just say, in general, to determine if, so here's our general quadratic equation, or quadratic expression, ax squared plus bx plus c. So I'm not saying that this is equal to 0. I'm just saying, let's say this is a quadratic factor that we have, right? And we want to know, if we're not sure, maybe again we're not so good at factoring, and we want to know for sure, can this be factored further? Well, to determine if, come on, so to determine if ax squared plus bx plus c is irreducible, or is it reducible, we use the discriminant of this quadratic. And the discriminant is that expression that shows up under the square root of the radical in your quadratic formula, that b squared minus 4ac. And it turns out if this b squared minus 4ac is negative, then the quadratic can't be factored any further using real numbers. Because think about it, you get a negative number under your square root, that's going to lead to complex numbers. We don't use complex numbers in this course, so we just say that, okay, we're going to stop at whatever that quadratic is, right? So here's sort of the rule. In fact, I'll tell you the 3 possibilities. So if b squared minus 4ac is greater than 0, then it means that the quadratic must have 2 linear factors, right? So it must have 2 simple linear factors. Again, not necessarily using integers, right? But if your discriminant ends up being a positive quantity, then it means you can factor it further. If the discriminant is equal to 0, so if your b squared minus 4ac is equal to 0, then that means you have a repeated linear factor with multiplicity 2. So you have a linear factor with multiplicity 2. Right? So again, it's like it would end up being like one of the previous ones that I gave examples of. Now, if you compute your discriminant, your b squared minus 4ac, and you get a negative number, then this means the quadratic can't be broken down any further using real numbers. So if this is the case, then we have an irreducible quadratic. right? And depending on which of these, again, we take a slightly different route in our partial fraction decomposition, right? So you might then ask yourself, well, what about, so we have linears, we have quadratics that can't be broken down. Well, does that mean we might have third degree polynomials that can't be broken down, or fourth degree polynomials that can't be broken down? Well, it turns out that that can't happen, and this is one of the fundamental results from algebra. It's actually a theorem, and I will state the theorem now. And it's sometimes referred to as the fundamental theorem of algebra. Right? Our famous mathematician Gauss proved a version of this. So this is the fundamental theorem of algebra. And this is what it says. Let p of x be a polynomial. So let's say we have a polynomial of degree n. Come on, of degree n. Right? Then p of x has a complete factorization. So meaning fully factored, so a complete factorization that consists of linear and irreducible quadratics. Right? Over real numbers. So over real numbers. Right? Moreover, so additionally, the sum of all the multiplicities of all the factors, so if you add up all the multiplicities of the linear factors and all the multiplicities of the irreducible quadratic factors, they have to add up to n, right? So the sum of all multiplicities come on. So the sum of all multiplicities is n. That's the degree, right? And so the idea is that every polynomial, no matter what the degree is, can be factored or has a complete factorization where all the factors are either linear or irreducible quadratics. And some of them might be repeated, right? So that there's no wondering, well, what does it look like for third degree or fourth degree? So we basically, once we understand the types of linear and the types of irreducible quadratic factors we can have, then that essentially describes all the possible factorizations of polynomials. And that really is a remarkable result, and we can thank Gauss for that, right? So that, in a nutshell, is that's our little trip down the algebra memory lane. I don't know. Hopefully, some of these concepts would kind of ring a bell, and then and this is just a matter of you getting a refresher in these ideas. Hopefully, they're not completely new, because then that makes the process of partial fraction decomposition that much trickier. And what we will do starting in the next video is go through, like, case by case, what to do when certain types of factors show up in our rational functions. So we have to understand the types of factorizations that are possible to then understand when and why we do what we do in our partial fraction decomposition. So I'll see you then.